Chapter 7, Transverse Shear, Maximum Shear in a Circle and Triangle. So just consider we have a solid circle like what you see here, and we want to calculate the maximum shear and its location. So a solid circle with the radius of capital R handling a vertical shear capital V. Mhm. We do know the formula for tau average is VQ over IT. And if, and at the same time, we do know the maximum shear happens either at the minimum thickness or maximum first moment of an area. So if we go by the maximum Q, we can get the maximum shear. So let's see how that works. I for a solid circle is a quarter of pi r to the power of 4, and just assume capital R and lowercase r, both of them are stands for a radius. Uh, Numeric value of shear is provided, or it's given like parametric. The thickness is the, let's get back to that one, and that's considered at 2r a diameter. And why is that? Q is a prime y bar prime. Do you remember we told we are going to calculate maximum shear, so we need to go by maximum Q, and maximum Q is just goes by a, if you consider a half of a circle as your area, a prime as your element of area, that Q is a prime times y bar prime, and that goes by a thickness, the thickness that shear applies on that is 2r, or a diameter of the whole circle. So how about y bar prime? That's a distance of a centroid of semicircle to the center. So what is that? If you remember, that's 4r over 3 pi. If you just plug the area for r a prime, which is a half of pi r square, times 4r over 3 pi, and do the math, it gives you 2/3 of r cubed. Mhm. And if you just replace that in formula for tau max, uh-huh, it and simplify the equation, it just gives you 4/3 of shear over the area of the entire circle. Mhm. So tau maximum for a solid circle, mhm, goes by an area of a semicircle as an a prime to give you the maximum Q, and that maximum Q develops maximum shear. mm, And that's 4/3 of shear over the area of the circle. Let's see how is that in a triangle. So just assume we have a triangle and we just want to know what is the maximum shear again, and what is tau max, and also its location, the location of maximum shear. Mhm. In such case, let's consider again an area of what? A prime. Hmm? For our element, that's for Q. Q is A prime times Y bar prime. So first of all, we need an element which stands by a distance of y, mhm, from the neutral line, which is the centroid for the whole triangle. And the neutral line or centroid for the whole triangle is 1/3 from base, 1/3 of h from the base, and 2/3 from the other, mhm, part. So if we know our element width is b naught, mhm, and again this is the centroid for our element, and it's located at a distance of y from the centroid of the entire area. Mhm. So again, formula for tau average is VQ over IT. Let's see how we can calculate tau max. Mhm. Q is A bar times A prime times Y bar prime. Mhm. For A prime, we simply know that's the area of our small a prime over here. So that's a half of b naught times a times the height of that, and the height is, so that's a half of b naught times, if the entire area for second for the top part is 2/3 of h and this part is y, so the height of our small element is just 2/3 of h minus y bar, 2/3 of h minus y. Mhm. So that's our h prime, for example. So that's the how we calculate the area for a prime. Let's see how to calculate y bar. So if you look at the y bar is the centroid of our element. So that's y from the neutral line. That's a distance of y plus what? If this is a 2h, if h prime is equal to 2/3 of h minus y, we just need a 1/3 of that for the centroid. So that's a 1/3 of h prime. So that's y bar, y bar prime. And if you just replace these two in Q and replace Q in tau formula, you have the tau average. And definitely what is our T here? Thickness is B naught. The thickness of our small elements. And at the same time, I, we do remember that I of neutral, I for centroid for a triangle is a 1 over 36 b times h cubed, isn't it? I will provide you with the link to a video related to calculation of a moment of inertia of a, a triangle or different shape based on parallel axis theorem as well. So that's IC. So I do know what I is. I have T. V should be provided. So V is all the time a vertical shearing force apply at the top or in the middle. And we just calculate Q. If we just replace back in the main formula of tau average, we have tau average in a parametric format. So by replacing that in formula, again, this is a bar for a triangle based on centroid, and B naught is the thickness of our yellowish element at the top. Mhm. If you do so, and at the same time, the area for the whole entire triangle is a half of b times h, and tau average, if you rearrange the equation, bring 36 from the denominator to the numerator, it's a 36 over 6, and it just gives you this equation. Mhm. And if you simplify that equation, it gives you tau average is V shearing force over the entire area for the entire rectangle, not only our element, times this equation, mhm, based on H and Y. And at the same time, tau max is a d over dy of tau average when it goes to zero. If we make a derivation of tau average and make it equal to zero, that gives us a tau maximum. Hmm? Let's see how that goes. And that was an important part of this solving this equation. And that's all. We do that all to get what the y is. Mhm. We are looking for y to replace that in the main formula and get the tau maximum and also the location. So in that sense, tau average is this formula. Tau max is a d over dy of tau average when it goes to zero. Mhm. And if we know these two facts, that tau average is this equation and tau max is just a d over dy of the above term. So it just gives me 2 over h minus 12h squared times y goes to 0. That's the derivation of the top, d over dy. And by having that, it just simply gives me y is equal to h over 6 from the neutral line, because our calculation were all based on the neutral line. Our moment of inertia was based on a neutral line for the entire system, so entire triangle. So it gives us a y is equal to 1/6 of h, mhm, from neutral line. If you just plug in y equal to y is equal to h over 6 in tau in the main equation of tau, vq over it, it gives you tau maximum is equal to just I bring the numeric value h over 6 there, and by a rearranging and work around the equation, it gives you 9 over 6 times v over a. So if you simplify that, it's just tau max for a triangle. It's a 1.5 v over a. Mhm. And it was interesting results. So why? Because it just says in triangle like a rectangle, tau max is a 1.5 times volume over area. So if we have a rectangle and we have a rectangle and triangle with the same dimension of area, with the same volume of with the same amount of shearing force, and the tau max at both of them are equal to 1.5. Mhm. And the other interesting result is the location of maximum shear is actually at the center, because h over 6 was calculated from centroid, and from base we do know the neutral line or centroid of a triangle is located at 1/3 of h. So h over 3 from base plus h over 6, gives me a 1 over h. So again, the centroid of a triangle is also located at its center by the numeric value of 1.5 shear over the total area. Thank you.